So at this point, if you've been watching all these videos, you've seen a lot of nucleophilic acyl substitutions. And it might seem like overkill to add one more in the category of acid-catalyzed hydrolysis of esters, but I can't avoid it because first it's so exciting that you're now at the point in chemistry where you can understand how a triglyceride, a fat molecule, breaks apart. And also because this reaction, seeing it in this biological molecule, illustrates something that you'll find more often as you transition from organic chemistry to biochemistry. And that thing that you'll find more often is that the molecules will look much bigger and much scarier, but the principles behind how they react are exactly the same as what you learned in organic chemistry. So we've been seeing small esters. Well, here we have a triglyceride. And if you look at the products, it makes a little bit more sense of how this gets its name. There are two parts to a triglyceride. You have a 3-carbon molecule with alcohols on each carbon. That is glycerol. You can even see in the name, it's an alcohol, ends in an OL. The next thing you'd notice is you have these long hydrocarbon tails in these other molecules. Those long hydrocarbon tails don't contain any polar bonds. They don't have any very electronegative atoms or any big differences in electronegativity, which means they don't have slight positive and negative charges, which means they are non-polar. Remember, the poles are the slight positive and negative charges. So if you don't have those, then the molecule is non-polar. Now, water is very polar. It has charges on every atom in it. The oxygen is slightly negative, the hydrogens are slightly positive. And so these non-polar tails will not mix with water. The principle for solubility is like dissolves like. Polar solutes dissolve in polar solvents. Non-polar solutes dissolve in non-polar solvents. It's as if you took, if you try to imagine this mixing with water, imagine a whole bunch of water molecules. It's as if you took a sort of big Tupperware container, and all of the polar molecules are like little magnets, and all the nonpolar molecules are like poker chips. And you shake them up, all the magnets will stick together, all the polar molecules will stick together, and all the nonpolar molecules will be excluded from them. So they won't mix together, they will separate, and like will dissolve like. These nonpolar hydrocarbon tails are fatty. The word fatty is referring to their solubility. Fats and oils fall under a bigger umbrella called lipids, and lipids are any biological molecule that does not dissolve in water. So any non-polar biological molecule is a fat or an oil. And so here, these long tails are fats and oils. Now if you look at the other end, at the very end of those tails on each of these things, you have carboxylic acids. And so here, carboxylic acids, here what we have ultimately are fatty acids. Fatty acids are long hydrocarbon tails with a carboxylic acid at one end of them. And the only difference between different types of different types of fatty acids, the difference between linoleic acid and arachidonic acid, or oleic acid, palmitic acid, the only difference are the tails. How many carbons are there? How many double bonds do you have? Where do you have the double bonds? That's the only difference between all the fatty acids. So if you take 3 fatty acids, so you'll notice we've got this one on top, one in the middle, one on the bottom, 3 fatty acids, and put them on glycerol, then you get a triglyceride. Okay, well that's what we have here. And notice what the overall change is in this reaction. The triglyceride is a triester. carbon double bonded oxygen, single bonded to an ether. Carbon double bonded oxygen, single bonded to an ether. Carbon double bonded oxygen, single bonded to an ether. You have 3 esters. So it's a triester. All 3 of those esters come apart, give you 3 carboxylic acids and 3 alcohols. Now all 3 of those alcohols happen to be on one carbon chain, but there you have it. And so if you've been following along with the videos for the simpler molecules that we've seen before, the process was the same. We took an ester and turned it into a carboxylic acid and an alcohol. The only difference here is the long carbon chains. Now, this is one other interesting point, I think, to make, because you might just be tempted to view this bigger molecule as just an encumbrance, as an obstacle. Like, why? I mean, it's the same reaction, just more confusing because you have that big thing there. So you might even grow to resent those big chains. But I urge you to resist the temptation. These structures are fascinating. These bigger structures that you'll run into over and over again in biochemistry are different from organic chemistry. In organic chemistry, people were trying to find the simplest reagents to use to make something happen. And with life, these molecules were not chosen because they were simple. They were chosen for historical reasons. You often think of fossils as dead things, but everything that appears in a living cell, every molecule of life, is a fossil. It's there because of some past event that put it there. And so all of these larger structures that you see in biological molecules give you hints about the history of life. And so they're exciting in that way, even if they are confusing to look at first, and they certainly take more time to draw. Okay. One final point. Notice the power of functional groups. The functional groups are those groups of atoms that always behave or function in the same way. Esters, carboxylic acids, alcohols, etc. Once you know those, it doesn't matter how complicated or big the molecule is. You'll know how it reacts. Add an acid to an ester, you always get a carboxylic acid and alcohol. Wait, what about this long hydrocarbon chain? Nope, doesn't do anything with that. There's no functional group there. So, those are just some big conceptual points. Now we can dive in to, now that we have some terms for these things, we can dive into how this reaction works. It's going to work in the same mechanism we've drawn before, nucleophilic acyl substitution. So if we just zoom in on one, and I'm only going to draw the mechanism for the hydrolysis of one of these esters, the mechanism for the hydrolysis of the other 2 is exactly the same. So you can just watch the video 3 times if you want to see the mechanism for the other 2. But the mechanism for the hydrolysis of these esters is the same. It's nucleophilic acyl substitution. You have a leaving group. Here, the leaving group is the ether part of the ester. And you have a nucleophile. And the nucleophile here is going to come from hydronium. And we run into a similar situation as we did in the last 2 exercises. The nucleophile we have, first of all, the nucleophile, what's supposed to be the nucleophile has a positive charge. So that's immediately a problem. Nucleophile is supposed to have a negative charge. So we're going to have to do some proton transfers with that. Fine. But even if you look at the ester, the carbonyl carbon looks like it's slightly positive, and it is slightly positive. It is slightly positive, but the lone pairs on the oxygen are allylic to that pi bond. And so they can act through resonance. Through resonance, they always act to make a sort of double bond here. Well, it's not a double bond. Both of these bonds are something in between a single and a double bond. But that lone pair can move electron density toward the carbonyl carbon to help stabilize the positive charge there, meaning that that is not the strongest electrophile. You would need a very strong nucleophile to attack that. Or you can make it a better electrophile. And that's what we're going to do here. We're going to add this hydronium. And the hydronium is going to take this molecule that is not reactive enough. It's part of the reason why it exists as a storage molecule in living things in the first place. It's stable, so doesn't tend to react. It can stick around. It's not reactive enough, and we can make it more reactive by doing a proton transfer. Remember, proton transfers change the reactivity or the stability of things. So the slightly negative oxygen in the ester can attack one of these slightly positive hydrogens. The electrons snap back onto the oxygen there. So that's our proton transfer. And what we'll have after that first step, so let me draw that down here. So what we'll have after that first proton transfer step is the same molecule, just a hydrogen will be bonded to that carbonyl oxygen. It has 3 bonds, so it'll now have a full positive charge. And what was hydronium after the proton transfer will just be water. Okay. Well, what that does is this oxygen was before pulling electron density to itself because it was electronegative. But now it's pulling it because it's electronegative and it has this positive charge that's pulling on it. So it's stealing a lot of electron density, and the slight positive charge on the carbonyl carbon gets bigger. So this is now pretty big. So if you compare it with the one above, you can see how the slight negative charge became bigger after that proton transfer. In other words, the carbonyl carbon becomes a better electrophile. Well, what can attack that electrophile? Our nucleophilic oxygen of water. And so that oxygen can swoop in, attack the carbonyl carbon. Pi bond would break, sending electrons up to the oxygen to stabilize the positive charge there. Now, if we're going to step back and imagine what's happening here, we would classify that as a nucleophilic attack. We have our nucleophile attacking our good electrophile there. So nucleophilic attack, and after that nucleophilic attack, we will have our famous tetrahedral intermediate. So first, this pi bond will break. It won't be there anymore. It will go onto this oxygen as a new lone pair. So notice that oxygen had a hydrogen. It will now have a hydrogen and 2 lone pairs. Right? It had the 1 lone pair above. So that's that. And then we have this water attached to what was the carbonyl carbon. Now that now that oxygen has 3 bonds, so it has a full positive charge. And you may look at it and say, well, that's a pretty good leaving group. I mean, it can pop off and be neutral, and that's true. This exists in equilibrium with this structure above. But sometimes after it forms, instead of just popping off, something else happens, and it creates a new storyline in the journey of this molecule. So those charges always give you information about reactivity. Now, in this case, we want this nucleophile to stay there. This is our nucleophile that's going to be replacing our leaving group. So we want it to stay there, and it's very reactive right now. It's ready to pop off the molecule at any second. So how do you make it less reactive? How do you change the reactivity of a molecule? You do a proton transfer. So we can take another water molecule from the hundreds of trillions of billions of them in the solution, jostling around that water molecule. Sometimes the oxygen smacks into the hydrogen. The slightly negative charge sticks to the slightly positive charge, pushing the electrons in the bond onto the oxygen there. And so you see that proton transfer happening, the hydrogen going from one molecule to another. And what we have after that is so we still don't have this pi bond here. That oxygen is bonded to a hydrogen, has 2 lone pairs. But now, instead of an H2O on the, what was the carbonyl carbon, we have just an OH after that proton transfer. Okay, so now we have our famous tetrahedral intermediate. It's stable. We don't see any charges there, and we've accomplished 1/2 of what we have wanted to do. We wanted to do a nucleophilic acyl substitution. We wanted to replace our leaving group, the ether oxygen, with our nucleophile, the OH oxygen. So we've done half of that. We've put the nucleophile on there. We just have to kick the leaving group off. But if you look at this leaving group, it is right now in green. It is a bad leaving group. If it were to leave, if it were to pick up its bags and say, you know what, I don't need all this talk. Everyone's calling me a leaving group. Why do I need to stay on this molecule? If it were to leave, that oxygen would have a negative charge, a full negative charge, which is very unstable. And so it would snap right back on to the carbon that it left off. So we have to turn that into a better leaving group. And we can do that by doing a proton transfer. Right now, it's not a good enough leaving group. In other words, it's not reactive enough. It's too stable. So how can you change the reactivity or the stability of things? By doing a proton transfer. So let's draw that in. We're going to do another proton transfer here to turn that leaving group into a good leaving group. So we have hydronium that formed here, that when water accepted this H+, we got a hydronium molecule. And the slightly negative oxygen in this ether, in the ether part of what was the ester, can steal one of those slightly positive hydrogens. The electrons sling back onto the oxygen to stabilize the positive charge on hydronium. And what we have now is a bad leaving group that turned into a good leaving group. So let's recap all these changes as I draw here. This pi bond broke many moons ago to give us a H and 2 lone pairs. We have our stable OH here. And now, after this most recent proton transfer, this only has 1 lone pair, and it has the hydrogen there. And notice that oxygen has 3 bonds, so it will have a full positive charge. Well, now it's a good leaving group. Now, if it takes electrons to it, those electrons will just stabilize the positive charge. They won't create unstable charge of their own. So all this needs is a little push, and it'll pop off of what was the carbonyl carbon. And the push comes from the lone pairs in the oxygens. The carbon here is bonded to 3 oxygens. It's losing electron density to 3 atoms. So it's really slightly positive. And that's very attractive to these slightly negative oxygens, which have these extra lone pairs on them, these 2 lone pairs on them. So those lone pair electrons are attracted to that slight positive charge and would like to form a pi bond to them. You could use either one. These are technically identical. I'm going to use the one that was originally in the carbonyl. So this lone pairs here would snap back down, try to create a pi bond, and now that you have a good leaving group, it works. It kicks the leaving group off to make room for its new pi bond. And so if you were to try to classify that in one of the 4 curved arrow patterns, you would classify what's happening here as loss of a leaving group. Okay, well, what do we have after this? We have 2 things. We have not a triglyceride anymore, but a sort of diglyceride. 2 fatty acids on a glycerol chain. So this is not going to be here. Oops, this is not going to be here anymore. It's leaving the molecule. And that oxygen, you'll see, has this hydrogen on it. So we've turned that into an alcohol. The other piece that we have is our chain. And so that will have left the molecule. Notice that this OH becomes this OH here, and the carbonyl becomes this. Now the one thing we have to include here is this bond to the hydrogen, which means that that now has, because it has 3 bonds total, that oxygen has a full positive charge. So we're almost done. We've removed 1 fatty acid from the glycerol backbone, but we have to stabilize that fatty acid. And the way, because right now, because of this positive charge, this is a really good electrophile, and this can attack it again, which is why we have this equilibrium here. So we just have to stabilize that, and we can stabilize that with some water. We formed water in this previous step here, and so water can come in. The oxygen is slightly negative. It attacks the hydrogen here, which is slightly positive. The electrons snap back onto that oxygen there. And the 2 products that we get are going to appear to be what I'm about to draw. So this hydrogen won't be attached there anymore. That bond will turn into a lone pair, which stabilizes that positive charge. So that hydrogen went over to water through the action of that curved arrow to turn water into hydronium. So you'll notice you have this acid catalyst reappearing again. We started with an acid catalyst, we end with it. We needed it to make the reaction happen, but it doesn't get used up. That's the definition of a catalyst, something that speeds up a reaction without getting used up. And in biology, that's mostly going to be enzymes, but in this case it's an acid. Molecules that speed a reaction up but don't get used up. And what we end up with is one alcohol and a carboxylic acid. A fatty acid has been removed from glycerol. If you wanted to summarize this last curved arrow pattern, we made this molecule that was too reactive or too unstable, we made it more stable by doing a proton transfer. Now, because the molecules are really big, I don't know if I'll be able to see all these steps from this far out. You can kind of see them. You'll notice they're the same. You still have the nucleophilic attack and the loss of a leaving group. There's essential steps in any nucleophilic acyl substitution. In addition to that, we had a proton transfer at the beginning to make the ester more reactive, the carbonyl carbon in the ester a better electrophile. We had proton transfers in the middle to stabilize the nucleophile after it arrived and to make the leaving group a better leaving group. And we had a proton transfer at the end to stabilize the final molecule we made. And so you can see how in that process we removed this ester, we took that apart and formed the alcohol and the carboxylic acid. And that same procedure would happen to the other two esters. And in your body, all of these procedures would be happening at the same time in this sort of brilliant cosmic dance of molecules. Every time you eat a meal, you have some sort of triglyceride in it. You can think now about what's happening in your stomach when you digest these triglycerides. This nucleophilic acyl substitution, this hydrolysis of esters, this acid-catalyzed hydrolysis of esters applied to a biological molecule.